Hey boys and girls, meteorologist Steve Caparotta here, back with Cap's Corner Summer Camp. It's the final lesson, the final episode of the summer, episode number 8, and we're going to talk all about how people like me, meteorologists, how we actually arrive at and make our weather forecasts. I do need to say a special thank you to HMC Generators for sponsoring Cap's Corner Summer Camp throughout the summer, and we'll talk about at the end. If you missed the lessons, there's plenty of spots where you can go back and find them. Now, as meteorologists, we're used to seeing and hearing things like this, and the moms and dads that might be watching today, maybe some of you have even said or thought things like this, but the idea is that many people think meteorologists and forecasters, we just kind of guess at what we're doing, right? But to be fair, there's a 50% chance of just about anything is what this little cartoon says, implying that we guess. And there's even stuff like this, kind of implying that meteorologists, we lie, we make it up, we're Pinocchio. But in reality, boys and girls, weather forecasts are actually pretty good, and they keep getting better as time goes by. This is just one article I pulled from a couple of years ago, but the headline says modern weather forecasts are stunningly accurate. And I'm going to show you that. I'm going to give you hard numbers to prove that maybe despite what some people think, weather forecasts are pretty good and they continue to get better with time. My favorite way to show that is using the forecast accuracy for hurricanes. Now, this is kind of a busy looking graph, I know, but I'm going to explain it to you. It's not that complicated. It may look kind of complicated. It's really not that bad. These are the average forecast errors for the National Hurricane Center when they're forecasting a tropical storm or hurricane, how far off they are in miles. So if a storm is approaching the coast, do they miss the landfall by 25 miles, 50 miles, 100 miles? And we average those through time. But the takeaway, as you look at this graphic, do you see how everything is slanting down from the top left to the bottom right? What that is showing us is as we go through time, the errors are getting smaller and the forecasts are getting better. Let me summarize that for you. So today's 5-day tropical forecast, tropical storms and hurricanes, they're as accurate as a 3-day forecast was in 2008, just 13 years ago. That's pretty quick improvement. They're as accurate as a 2-day forecast was in 1998, about 20 years ago. So again, that's some hard, cold facts on how hurricane forecasts have actually gotten much better with time. If we look at a 3-day hurricane forecast, it's as accurate as a 2-day forecast was just 7 years ago, and it's as accurate as a 1-day forecast was less than 20 years ago. So again, hurricane forecasts getting much, much better as time goes by. And I think if you pay attention to hurricanes, you'll see that the track forecasts, generally speaking, are getting really good. Now, every once in a while, there's going to be one that's off a little bit, but most of the time, we're doing really good. Now, the improvement on the strength, the intensity of the hurricanes, those forecasts has been a bit slower. We're still seeing improvement. You still see how these lines slant down from the top left to the bottom right, but they don't slant as much, right? So there's some improvement. It's just not happening as quickly, but still getting better at that. There are a lot of really smart people at trying to make those intensity forecasts even better. But I think those two graphics do a great job showing how hurricane forecasts have actually gotten a lot better, not only in my lifetime, but just in the last 15 to 20 years. This is another kind of busy looking graphic, but this one is focused in on high temperatures. This is from the Weather Prediction Center, which is kind of tied to the National Weather Service. And each one of these lines represents whether it's a 3-day forecast, a 4-day, a 5-day, 6-day, 7-day. But again, you see how with time we kind of see everything's kind of trending down. That means our errors are getting smaller as we go forward in time. And just give you an idea, a 5-day high temperature forecast today is about as accurate as a 3-day high temperature forecast was in 2008. So again, less than 15 years ago. So weather forecasts, despite what maybe some of your moms, your dads, your grandparents will tell you, they are getting better. And that's not about me or any particular meteorologist. The science is getting better, the technology is getting better, our computing power, our computers, we can do more with them. It's getting better. So I just wanted to give you a look at that because that's one of the perceptions, one of the misconceptions that we have to fight on a daily basis. Now our forecasts, they start by gathering a lot of current weather information. Look at all this stuff that we use to gather current weather information. So that includes maybe the most obvious things, our weather stations down on the ground. I'm going to show you an example in just a moment. We have weather balloons. I've got an example of that to show you. Weather satellites, we had a whole lesson about those. Airplanes, we actually gather weather information from the planes flying through the sky. Dropsondes, what is that, you say, Mr. Steve? Well, I'm also going to show you what a dropsonde is. Buoys, if you haven't heard of those, I'll give you a picture of a buoy. And even ships out over the ocean also gather weather information. There's even more stuff on this graphic, but those are just some of the things that we use to gather current weather information, which is really important in trying to make a forecast. So here's what an actual ground level weather station looks like, one of the National Weather Service weather stations. And there's actually a number of separate pieces of equipment that go into it. So what is all this stuff? Look at that. So here's our rain gauge over here. We've got one that gives us the temperature and the dew point. The dew point measures how much moisture is in the air. The one that's labeled current weather, what do I mean by that? Well, this is a sensor that actually automated tells us if it's raining, it's snowing, things like that. Excuse me. Then you'll note in the middle, the taller thing, that's the anemometer. An anemometer is what measures the winds, okay? Notice that one is higher up. So our wind speeds are actually measured at a height. The standard height, the most common, is 10 meters or about 33 feet above the ground. So winds are actually measured a bit higher up. Ceilometer, what is that? Well, that tells us how high the clouds are, so there's a separate sensor for that. We've got a separate sensor just to tell us if there's freezing rain around. Do you remember that? Freezing rain, we talked about our lesson, different types of precipitation, and then we've got one that measures visibility. How far can you see? So lots of different things go into our ground level weather stations. Here's a look at one of our weather balloons. This is from the National Weather Service in Slidell, our local office. These are launched twice daily. This happens all over the country and a number of spots around the world. But the great thing about weather balloons is they give us weather information all the way from the ground up to nearly the top of the atmosphere. They can go as high as 20 miles up. But as they go up into the sky, depending on what the winds up above us are doing, they also kind of drift away from where they were launched, and they can drift 100 miles or more away from the launch spot. And I'm going to give you a look at one of these weather balloons being launched. Now, this was during Hurricane Irma down in Key West. This guy, I actually went to college with this guy back in the day, but he's fighting the big winds to launch this weather balloon. You can see that because if that balloon hits anything, it's going to burst, and then we don't get the weather information. And these things are not cheap, so it's kind of stressful when you have to do it in bad weather. But as you see, he's about to let it go here in a second, fighting the winds to let that go, and eventually he does. So attached to that balloon at the bottom is weather equipment. It measures the temperature, the wind speed, the humidity, and sends that back via radio signal as it makes its way up into the atmosphere. Now, we talked about weather satellites. We had a whole weather lesson on that, so I'm not going to spend a lot of time on this, but we have our geostationary weather satellites. These are the ones that stay over the same point on Earth at all times, and that way we can string several images together and make a movie and see how clouds are moving. And then we have our polar orbiting satellites. These are the ones, as the name implies, that orbit over the poles. But we can actually gather current weather information from our satellites, and some of that gets input into our weather models that help us make a forecast. And I'm going to show you more on weather forecast models in just a second. Now, I mentioned in our list of things that we use a dropsonde. What is a dropsonde? Here's what a dropsonde is. That's what it looks like. So it's a tube, it's attached to a parachute, and that tube has some weather equipment that again will measure things like temperature, humidity, wind speed, the air pressure. and it's dropped from an airplane, and as it's falling down to the ground, we'll radio that information back and give us an idea of what the weather is doing. So these dropsondes especially get used a lot in hurricanes. So I'm going to give you a look at this. So the hurricane hunters, they'll head out. They'll fly typically what's called an alpha pattern. It's kind of similar to the Greek letter alpha. But you see here, as they're flying through a hurricane, they drop a number of these dropsondes. This is a P3 hurricane hunter plane. You see here at the bottom of the plane, there's a little chute. Watch. There goes the dropsonde. There's somebody in the plane that actually lets those out. It falls down, attached to that parachute. Eventually, it'll splash right on into the ocean. But as it's dropping down to the ocean surface, it's measuring constantly the temperature, the wind speed, all that stuff, and relaying it back. So that can help us kind of fill in some of our data gaps. We can't put ground weather stations out over the ocean, right? So those dropsondes really help, especially when it comes to hurricanes. These things right here also help us out over the ocean, and with hurricanes especially. This is what a buoy looks like. So most often, these buoys are actually kind of anchored down to the ocean floor, and they stay in the same place. So they measure the wave height, the winds, the temperature, and many other things. So this really helps us out because we have a lot of weather information over land areas. We don't have nearly as much out over water and over the ocean. So these buoys help us fill in some of those gaps. And talking about the gaps, look at this map behind me. So what are we looking at here? Well, this is essentially a map of the world. And everywhere you see a green dot, that's where there's a weather station. So there's a couple of important things to note. Number one, when you look out over the oceans, the blue, we don't have many weather stations, right? So we have big gaps in our weather data there. Number two, many land areas, like where we live in the United States and North America, tons of weather stations just covered with those green dots. But there are even land areas that don't have a lot of weather stations. Northern Africa, around the Sahara Desert, big parts of Asia don't have a lot of weather stations. As you go up Greenland, Iceland, towards the North Pole. So even over land, there are data gaps when we try to gather our weather information. So we try to supplement the weather data, try to get some additional weather data the best that we can. One way we can do that is by airplanes, attaching weather equipment to airplanes. So what this map here is showing us is the flight paths of airplanes that are actually gathering weather information. So what you'll see is, can you kind of see where it's yellow, orange, and red right here? That's the United States. We have a lot of planes constantly up in the air over the United States. And even though we have a lot of ground level weather stations, the airplanes, a lot of the airplanes will still gather weather information up in the sky as they fly over. But where the airplanes really help, out here over the Atlantic Ocean, where we don't have a lot of weather data. As they fly from, say, the United States over to Europe, a lot of those planes will gather weather information, and other spots. They'll fill in some of those data gaps that we have. Now, once we gather all of our weather information, it's time for the computer models to do their work. Now, how do the computer models work? This gets a little bit confusing, but we'll try to break it down to you. So if we take a look at the globe, you see how we've got all these squares here. This is what we call a grid. So for the boys and girls that are old enough watching this, if you've ever used graphing paper at school, imagine if we took a sheet of graphing paper and kind of wrapped it around the globe. We could break up the globe into little squares. So what we try to do in our weather models is we break the globe down into these little squares, and we try to represent the weather in each square. That's how we start out with our weather models. But not only do we have to do that down at the surface, we have to do that from the ground up into the sky, and that's what this is trying to show here. There are multiple levels in the atmosphere that our computer models also have to forecast. So here's the basic process for our computer models, though. They take in current weather information, all that stuff I told you about that we gather. Then the computer models, they do a lot of math. Meteorology and weather is actually driven by math and equations. For the kids that have done equations, we use these supercomputers that do thousands and millions of calculations to eventually help us arrive at a forecast. Once they do those calculations, the computer model produces a forecast. From there, people like me, meteorologists, we take those computer model forecasts, and that's not enough. We can't then just say, all right, to you guys at home, here's what the weather's going to do. We then interpret what the computer tells us. We add in some of our personal experience. We add in knowing that some models do better with certain things than others, and then eventually we make our own forecast with the help of what the computers have shown us. So I'm going to give you an example. This is from a recent day here in Baton Rouge. Computer models, you can look at them in all sorts of different ways. We can get maps of cloud cover, of rainfall, things like that. But we can also get output like this. Computer models will tell us what they think the high temperature is going to be, the low temperature is going to be, and what the chance of rain is going to be. So on this given day, one model, the GFS, said the high temperature in Baton Rouge is going to be 91, the low temperature 74, and we say a 59% chance of rainfall. Contrast that with another model, the NAM. It had a high of 94, a low of 77, and an 18% chance of rain. That's a big difference in those rain chances, right? 59% or 18%, and then the temperatures, there's a few degrees difference. So that's where the meteorologist comes into play. I have to use my experience to kind of interpret the data and figure out what I think is going to be best. Often what ends up working out best is some combination of all the computer models. So we have the National Weather Service has created in recent years what's called NBM, the National Blend of Models. They take a whole lot of model guidance, kind of blend it all together, average things out. And so for that same given day, here's what the National Blend of Models said: a high of 94, low of 76, and a rain chance of 49%. So typically, a good forecast, is going to be a little closer to this National Blend of Models, although it's got its own strengths and weaknesses as well that people like me, meteorologists, have to understand. Have you boys and girls ever watched The Price is Right? Have you ever seen the game Plinko?
Here comes tip number one, 10,000 in the middle, 10,000 in the middle.
Well, I'm going to show you how we can kind of explain forecasts using the game Plinko, okay? So let's pretend our little disc that they drop at the top of the game. This is represents the current conditions in our weather right now. So if we start out with our current conditions in weather and we pretend this is going out in time as we go down the Plinko board, there's a number of different paths our weather can take, right? Starting from here, depending on how things go. But when we look at model forecasts, any single computer model is only going to give us one path on the Plinko board. It's not going to give us multiple scenarios, different paths. It's only going to give us that one. But in reality, as we start to drop our Plinko disk, or if we go from, say, today into tomorrow, a small change in the weather can all of a sudden change the path of our forecast. So what the computer model was showing in blue, the next day can change just because of a small change, okay? So as we get closer to what we're trying to forecast, then the number of available paths, the number of possible scenarios becomes smaller, and then we can start to get a better idea. In this case, we're looking at potential rainfall, so we can start to get a better idea the closer we get to the end of the forecast. So we started out 10 days before. Once we get within 3 or 4 days of a weather event, we usually have a much better idea. But the idea from looking at this Plinko board is it only takes a small change in the conditions to have relatively big changes in the forecast. Now, one thing we can do in weather is use Ensemble model forecasting. You boys and girls, some of you might have seen a map like this. So we take the European computer model, and then we can run these ensembles. What happens is the modelers, they take the initial model, and then they just kind of tweak the conditions. Think about this like they go in the kitchen and say, oh, I'm going to change the recipe a little bit this way, a little bit that way. And they rerun the computer model 50 times, and then we get 51 different lines. In this case, we're trying to forecast Hurricane Zeta from last year. This gives us a little better idea of possible scenarios or possible outcomes. Now, as we contrast that with what the GFS ensembles were doing, you see a little more spread in the line. So as we look at these ensemble forecasts, one thing we're looking for, the closer those lines are together, the higher our confidence is in the forecast. And then in this particular case, you can kind of see there's almost two clusters, one that's clustered near South Louisiana, one that's more in Alabama or Florida. So what that's telling me as a meteorologist is, well, there's probably two realistic scenarios for this particular hurricane. One that would bring it more likely into Louisiana, one that might keep us off to our east, and it probably only takes a little bit of a change in the atmosphere to determine which of those scenarios ends up playing out. So hopefully it makes a little bit of sense. We also can use ensemble forecasts for temperatures and precipitation. It's just an example, but so we take the European ensembles, the European model will spit out a high temperature, a low temperature for a given day. Then we run those ensembles, 50 alternate scenarios, and then we can average it all together, and we'll get something like this. So this is an average of all 51 different scenarios, and often the ensemble approach is going to give us a little better idea of what's going to happen in reality. It accounts for a little more of the uncertainty that we deal with and gives us a better idea of possible outcomes. So hopefully it makes a little bit of sense. All right, that's about all I had on how we make weather forecasts. I could go on and on for this. So with that, I'm going to remind you as we wrap up, go to WAFB.com/CapsCorner. If you missed any of the lessons, you can watch them there. You can get all of our worksheets we've had to go along with the lessons. All the information is right there on that web page. With that, if you're watching on Facebook or YouTube, I'll go ahead and take any questions you have, pop them in the comments, and I'll do my best to answer them. All right, gang, welcome back. That was it for Caps Corner Summer Camp this year, the final lesson. I know maybe that one not quite as exciting as learning about tornadoes or hurricanes, something like that. But still, I think it's important to understand how weather forecasts are made, and also that maybe they're a little more accurate than what you might think. Yeah, there are good days, there are bad days in weather forecasting, no doubt about it. But the good news is, as time goes by, our weather forecasts are indeed getting better. So as I just said, remind you, if you've got any questions, go ahead and pop them in the comments on Facebook or YouTube, and I'll try to answer them. Taking a peek over right now, see if anybody has anything. Patricia says, we don't have a hurricane heading our way, question mark. No, we do not. So happy to report that. The only thing we've been tracking in the tropics has been a little weak area of low pressure just off the coast of the Florida Peninsula on the Atlantic side of it, not far from, say, Jacksonville. That low is drifting towards land this morning, expected to probably move ashore today without development, and that's really all we have out in the Atlantic right now. So we're doing good. But remember, if you're with me for my hurricane lesson earlier in the summer, one thing I did show is here in Louisiana, about 2/3 of our hits come in August and September, and actually September is our busiest month. So the heart of hurricane season is still very much ahead of us, so just stay alert. All right, let's take a peek over. Ryan on YouTube mentioned we joined late, so restarting the video for 5-year-old twins. Thanks for producing this. Happy to do it, Ryan. That's a great thing about YouTube or WAFB Plus. If you don't catch it live or you join a little bit late, you can always just back it up, start it over, and watch it at your convenience. So these lessons will be there, as I said at the end, also on our website, WAFB.com/CapsCorner. All right, just scrolling through. Derek is saying, when's it going to snow in Baton Rouge? Oh, I don't know, Derek. January 12th, 2022. Put it on the books, and we'll see what happens, right? But yeah, who knows? One other thing I did not mention, we do have worksheets to go along with the lesson once again this week, so that's on the website, WAFB.com/CapsCorner. So those are printable, downloadable, and printable. Go check those out, and all of them have answer keys, and all the ones from past weeks are there as well. All right, just taking one more peek, not seeing any questions rolling in, so hopefully we went through everything you guys wanted to learn about. So with that, probably go ahead and wrap it up. So hope you enjoyed having this around this summer. I enjoyed doing it. 8 lessons we went through. So we went through everything from hurricanes to tornadoes to the water cycle, all sorts of weather stuff, how we make forecasts. Again, if you missed it, if you missed any of it, want to go watch it or show your kids, go ahead and pull it up on any of those platforms and you can see it there. But we'll go ahead and wrap it up for now. Hope you enjoyed the rest of your summer, what's left of it at least, and we'll see you back on air for our regular shows.